Hi there, in this video I'm just picking up where I left off in the previous video due to a technical difficulty. I had to break this up into two videos here. So let's pick up where I left off. U is a subspace if it is closed under addition and scalar multiplication. Automatically though, it's going to inherit all the other vector space properties from this bigger vector space V that U is contained in, right? So all we're saying is that if you already know that the elements of a proposed, what you think might be a subspace, if you know that all the elements in that subset that you think might be a subspace are really contained in a bigger vector space V, you only actually have to check closure under addition and scalar multiplication and that the set is non-empty. It turns out it's going to inherit all the rest of those vector space properties. The other 8 axioms will automatically be satisfied just by the fact that everything in U was already in V. So this is a nice fact for us. If you have a subset of a vector space, you actually only have to check closure under addition and scalar multiplication, and that it's non-empty in order to show it's a subspace of V. Okay, so as an example here, let's let V be the subset of all matrices A in M22, so the set of real 2x2 matrices, such that the ijth element of A is 0. And I'm thinking of this for some specific I and J. It turns out it doesn't matter which one. For example, I could be 1 and J could be 2. That would say that we're talking about the set of all matrices such that the first row, second column is a 0 entry in matrix A. All matrices of that form with a 0 in the first row, second column would be in that set I'm describing. But it turns out it doesn't matter what I and J you look at, you're going to get the same answer here if you ask the question, is V a subspace of M22? Well, we know the set of all matrices in M22 of a certain form, certainly they're in M22, so they are actually a subset of M22, of this bigger vector space M22. Remember, we already discussed above, we didn't show it in detail, but we discussed how M22 is certainly a vector space. We're talking about a subset of that, of a certain form, right? Vectors within M22 that have a certain entry that's a 0. If we look at all matrices of that form, all we have to do is show that it's closed under addition and scalar multiplication. It's going to inherit the rest of the vector space properties from M22, where it lives. So to check this, we check closure under addition. In other words, let's say let A and B be vectors, really matrices, right? In our subset. All that means is that the ijth element of A is 0 and the ijth element of B is 0. All we want to show is that their sum is also of this form, right? The ijth element of the sum better still be 0 if we're going to claim that this is closed under addition. So what do we have? The sum of these two, we know by the rules of matrix addition to take two matrices and add them together is really just to add the corresponding entries of both matrices. So the ijth element of the sum is really the sum of the ijth element of A and the ijth element of B. Right? But we're saying for both of those, that's 0. So we do get, yeah, when we add these two, the result also has a 0 in that same ij element. Whatever I and j were, it doesn't matter. Whichever element we're specifying has to be a 0 to be in this subset. We're saying add two of those things, you'll still have a 0 in that element of your matrix. So yeah, we showed closure under addition. Closure under scalar multiplication is pretty similar. Just say for any scalar C, if we look at what happens by taking a scalar multiple, C times A, and we want to see what that ijth element is again, well, in this case, we know that to take a scalar times a matrix is really just to take the scalar times each individual entry of the matrix, right? The ijth element of C times A is just C times the ijth element of A. Whatever element's in ij, multiplied by C, right? But this is really just C times 0, right? Because aij equals 0. We know how to multiply scalars C and scalar 0. We just get 0. So, yeah, the scalar multiple must still be in V. You can also show very quickly that it is non-empty, V is non-empty, because the 0 matrix, we can very easily see, satisfies that the ijth entry is 0, and that's true for any ij we happen to look at, right? No matter which entry ij we're specifying would have to be 0 in order to be in set V, no matter which one, the 0 matrix certainly has a 0 in that entry, 0 in every entry. So, say this thing is in V, it's an element of V. So we've checked all our boxes, right? This is closed under scalar multiple under addition because B plus A is still in V. It's closed under scalar multiplication because C times A is still in V, and it's non-empty. And that's really all we have to show to conclude that V is a subspace. Of M22. Certainly all the vectors, which are really matrices in this case, all the vectors in V are certainly in M22. We said they're all the matrices that are in M22, and they have this specific form. So really all I've really shown here is that if you take a set of matrices that all have a certain entry zeroed out, the set of all matrices of that form will in fact be a subspace. Okay, so this is pretty standard. If you know you're not looking to prove that something's an actual vector space all on its own, if you know that these elements are in a bigger vector space already, you don't have to prove much. You just have to prove addition, closure under addition, scalar multiplication, and that it's non-empty. Let's go to the last page here. See a couple more interesting results. So similar to what we just did, you could actually show that Pn, I'll label it Pn here, which is commonly used to denote the set of all real polynomial functions of degree less than or equal to n, is actually closed under addition and scalar multiplication as well. And since this set of real polynomials is a subset of vector space we've already talked about, right? The functions defined on the reals, we know Pn would be a subspace just by showing that it is in fact closed under addition and scalar multiplication. To be clear, Pn, defined the way I've described it up here, really means P2 is the set of all functions of the form ax squared plus bx plus c equals your function. I should say this is f of x. Because this is the most general way you can describe a polynomial of degree less than or equal to n equals 2 in this case. It's a quadratic or less in degree, right? Meaning a could be 0, you're okay still having a linear function in P2, or even b could be 0, you just have a constant function in P2. And if c is 0, the 0 function is still a constant function, that's still in P2. So long as we don't take a higher degree, and it's still a polynomial, so long as we don't take a higher degree than 2, it's still considered to be in P2. Now, it actually turns out if you take a set of strictly quadratic functions, degree 2 polynomials, if you don't allow for the less than or equal to here, that will not form a subspace of the functions defined on the reals. And you might be able to think about why that is. If I took a set that contained only strictly quadratic functions, so something that cannot have a 0 coefficient on the squared variable here and no powers above that, if it had to be strictly quadratic, I could take a function minus itself in that subspace, and that would cancel out to the 0 function, which would not have degree 2. It would not be a quadratic anymore. So maybe you can see right away why we do need the less than or equal to part here to actually keep this as a subspace. If we said strictly equal to n in the degree, that would not be a subspace. Maybe you can play with that a little on your own. So this theorem here says if we let U be a subspace of a vector space V, then U contains the 0 vector of V. And this isn't maybe too astounding to us, but maybe it gives us back this sort of picture again, right? If I've got R2, a two-dimensional subspace, a two-dimensional vector space like Rn, then we already saw a subspace is a line through the origin, but it will always contain the origin of this bigger set. Likewise, if I take a plane or a line through the origin in R3, it will always, no matter what, contain the origin of R3, right? Both of these subspaces, whether it's a line subspace or a plane subspace, it will have to contain the origin of R3. That's really what this theorem is saying here. Right, and to prove that if we have a subspace of a vector space V, then that subspace contains the 0 vector of V, we can do it this way. Given any U in this subspace, we know that U is also in V, right? That's what it means that U is contained, is a subset or a subspace of V. That everything in U is really also in V. And so right away, since we know it's in V, we can apply the vector space properties of V to say that the 0 scalar multiple of U is the 0 vector of V, right? Anything in V, when we multiply by the 0 scalar, we get the 0 vector of V. Actually, that was by a theorem, not by a theorem over here. And that's just because V is a vector space. But we know that 0 scalar multiple of U has to also be the 0 vector in U, because U, in order to be a subspace, better be closed under scalar multiplication. Multiply by any scalar, including 0, it's still going to be in U. That's what it means to be closed under scalar multiplication. That requirement we had to make it a subspace. So we've got that, sure, the 0 scalar multiple of U is the 0 vector of V, but it's also the 0 vector of U. That means the 0 vector of V and U must be the same thing. You're really getting that what's playing the role of the origin in a subspace is really playing the role of the origin in the bigger vector space it's embedded in. It's not like two different elements can play that same role. Something can play that role for R3, but maybe a different element can play that role for a subspace of R3. It never works that way. The 0 vector in a subspace will always be the 0 vector in the larger vector space it's embedded in. Okay. So let's look at this example up here. Is the set W of vectors of the form absolute value of A plus 1, absolute value of A, absolute value of B, where A and B are some real numbers, doesn't matter what they are, so long as it is of this form for some A and B real, is that set a subspace of R3? Now certainly it's a subset of R3. Everything of this form, absolute value of A plus 1, absolute value of A, and absolute value of B, those are all real numbers. So this is in R3. But is it a subspace of R3? Is it closed under addition? Is it closed under scalar multiplication? And is it non-empty? Well, it turns out what we've set up here is actually equivalent to checking the non-empty requirement for a subspace. You can just check that the 0 vector of R3 would have to be in this set. Well, let's think, is there any A and B you could choose so that this vector comes out to equal the 0 vector? Let's set it up and see. The zero vector in R3 we're very familiar with. And now we're going to say, in order for these vectors to be equal, right away you can see from middle entries on both sides, absolute value of A would have to be 0, which we know this of real numbers means that A would be 0 itself. But if A is 0, then absolute value of A plus 1 is 1 here. It's not 0. So this doesn't work. We can never choose numbers A and B real so that a vector of this form looks like the 0 vector in R3. We can say the 0 vector is not in W. So W cannot be a subspace of R3. Right? It's usually a pretty quick thing to check. It's the thing I would check first when looking at a set of vectors and trying to figure out if it's a subspace. One of the first things I would try is to figure out if the 0 vector's in the set. If not, it can't be a subspace of any larger vector space. Okay, so let's look at a final example here. I mentioned we might see a kind of strange toy example to get you thinking more about what we said here, that if the scalars we use are real numbers, we call in one of these vector spaces, we call it a real vector space. But if all the scalars are able to be complex, if we allow that, we'd call that a complex vector space. And I said there are kind of weird, but still other examples we could look at, less common ones though. And so admittedly, the one I'm about to show you is not really relevant for us so much, but I want us to get a sense of how general this idea is. So consider a vector, or I should say a set of vectors, in which the only valid scalars are 0 and 1, and arithmetic on these follows this set of rules. 0 plus 0 would be 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1. Is this set, the way I've defined it here, is this set B equals just the elements 0 and 1, along with this definition of addition and scalar multiplication on its elements, is that a vector space? And I don't want to go through much of this, but maybe we can look at closure under addition and scalar multiplication and show that it's non-empty. I mean, we can see right away this set is non-empty. There are 2 elements in this set. There's at least 1, so it's non-empty. But what about addition? Let's see about closure under addition. Notice, let's say it this way, given, let's say it this way actually, there are only 2 elements in B, and there's only 2 valid scalars anywhere in our world that we can operate on, right? So we have actually laid out all the possible additions that could come from elements in this set. We could have 0 plus 0, both of those are in B. We could have 0 plus 1, both of those are in B. We could have 1 plus 0, those are both in B. Or we could have 1 plus 1, those are both values in B. And out of each of those, we get out, by this definition of addition, we get out something that's still in B. We get a 0 or a 1, depending on what we're adding. But no matter what elements of B we add together, 0, 1, 1, 0, 0, 0, or 1, 1, all those produce something that's already in B. We would say this is closed under addition with this rule of addition. Notice it's weird. 1 plus 1 equals 0 is not usual addition. So you might want to think about how weird this set is. It's very atypical. Well, what about scalar multiplication? We could show that. I haven't really showed this. I'm just kind of explaining it. If you can try to show it. If I take any element of B and I multiply it by any scalar, we have to be careful here. We are saying the only valid scalars, it's not going to be the whole set of real numbers or complex numbers like we described up here instead are very common. Instead, we're saying the only scalars anywhere in our world that we can deal with are the scalars 0 and 1. So what we have to test is, if we multiply anything in B by a 0 or 1, do we still end up with something in B? Well, we've got every possible multiplication in our world defined up here. If I take the first element of B, 0, I could multiply that by 1 or 0 because those are my only two scalars here. 0 times 0 is still 0. That's something in B. 0 times 1 is 0. That's something in B. 0 times 1 is 0. That's something in B. Likewise, I could multiply 1 by anything. I could multiply 1 by 0 or 1 by 1. And either way, I get something that's still in B. We do have closure under scalar multiplication. Now, checking the rest of the axioms is something I will leave to you. See if you can go through these axioms if you want extra exercise in this stuff, and see if you can go through these axioms and determine whether all of them are satisfied with this definition, this very strange definition of what may be a vector space. Very atypical vector space. Other things to consider that might be interesting. What about the set of all positive numbers, positive reals, the set of all positive reals, this is a new one, with the following definitions of addition and scalar multiplication. So the following operations. Let's say that adding two things in the set V is the same as multiplying them. And let's say that taking a scalar multiple of an element is really like exponentiating it, raising it to a power of C. What do we think? See if you can determine, with this rule of addition and scalar multiplication, see if you think the set V I've described is truly a vector space. Might be a good one to come to office hours with questions about if you'd like to explore it further. I'll say, is this a subspace of the real numbers R? Right, the real numbers R, that's like R1, that is a vector space. We're asking, is this a set of all positives? Those are certainly reals, but they're positive. With these operations, is that a subspace? I should be careful not to say a subspace of R because we don't have these usual definitions of addition and scalar multiplication on R. I'll just say, is this a vector space? So see if you can think about this question, solve it on your own, or come to office hours or email with questions about this. Probably a good way to get a sense of how general this idea of vector space really is. Okay, that's certainly it for this video. That's plenty for one section. We'll stop it there. Thanks.